Hello students, in this video lecture we'll learn about critical path method. We have already done two videos on the same topic, so it's pretty much clear already. So in this video I'll be just explaining the critical path method with one more example so that you come to know all the exceptional cases occurring in these kind of questions. So let's begin. We have already seen the network construction of a project. We have already seen how to compute earliest starting and latest completion time and determining critical activities and critical path, and then using this information to crash the project duration. By crashing we means reduce the project duration to a particular level which is asked in the question. So let's try all these things on this example. This is example 2 because one example we have already considered in the previous lecture. So in this example you can see that we are just given the project and two parts are asked. In the first part we are asked find the minimum cost schedule if project is to be completed in 28 days, and second part determine the crash schedule. So the first part asks you to give a schedule of 28 days while the second part asks you to determine the crash schedule. The meaning of crash schedule is it is that schedule beyond which a project cannot be compressed further. For example, the same project which we are considering in this example, say you can finish it in 28 days and then somebody asks, okay, reduce the time to 25 days. You say, okay, we can still do it 25 to 23 to 22, and so there will definitely come a time, there will become a duration beyond which you will say, okay, the project cannot be compressed further, it cannot be crashed further, or the project has reached its crash duration. So that's what the meaning of determination of crash schedule is. So we'll step by step go through all these parts. So firstly, we know the very first step, you have to draw the network diagram, and to draw the network diagram I just need this much information, the activities and the normal duration. So in other examples you see activities are denoted by A, B, C, D, E, F, but here in this example directly activities are given to you in the terms of numbers. So this kind of project drawing is easiest because you don't need to look at the predecessors or precedence relationships. Directly whatever are the nodes given to you, you can just follow them and draw your network. For example, you have to draw 1 to 2. So you will draw a node 1, a node 2, and then you will connect it with an arrow from 1 to 2 pointing towards 2. You want to draw 1 to 3, so 1 you have already drawn, you draw another node, number it node 3, and then join it with an arrow. Similarly 2 to 5, so that means somewhere definitely there will be a fifth node. So 2 to 5 we have joined, 3 to 4, so somewhere there will be a fourth node, 3 to 4 we need to join, and 3 to 5, so 3 to 5 has been joined, and 4 to 5. So you remember, it's not like you just first draw the nodes and then you make the connection. So whatsoever you follow, just learn to draw these networks by following the given activities. It's very easy. In fact, this is the easiest kind of networks to draw as I've just mentioned. And then below each activity, as you know, we write its normal duration. So 1 to 2 duration is 15. So you can respectively read all the durations and write there just above the arrows. So that's first step is done, network drawing. Then we know the very next step is to compute the duration of the project, which is also called normal duration. And to compute that, we need to compute ES and LC, earliest starting time and latest completion time. Since this thing I have already explained in even previous two videos, so I won't be explaining again to how to compute ES and LC. I assume you already know that. If you do not know, then you have to go back to the previous video lectures to learn how to compute ES and LC. So I have already computed here earliest starting time and latest completion times. The square box we write the earliest starting time, in triangular box we are writing the latest completion time. And you know, once this is done, so you have to look at the terminal node. So this is 31. So 31 is the total duration of the project. So duration is 31 days. You can see the unit of time from the given statement. All the data given to you is in terms of days. So duration is days. And now you want to compute the cost of the project. So how to compute the cost? This thing I have already explained you. You just add all the normal cost. Right now we are not looking at the crash cost, we are only looking at the normal cost. So you just add all these cost, you'll get 3900. So that's the normal duration and normal cost. So this is done. That means whatever is the given data, the project is going to be finished in 31 days. Now you recall what is the first part given to you. You're asked to find the schedule of 28 days. See the statement. Find the minimum cost schedule if the project is completed to be 28 days. Minimum cost schedule means obviously you will be taking wise decisions that 28 days you want to finish the project in, but this should be done at a minimum cost. So let's move towards next step. From this point onwards, we want to do the crashing. From 31 days, I want to go to 28 days. So let's see whether this is feasible or not. And what is the next step after computation of ES and LC? So I need to now identify my critical activities and critical path. So I have identified that these are the critical activities. Again, I'll say I have already explained you this part, how to identify the critical activities. So here you will see this 1 to 3, 3 to 4 and 4 to 5 are the critical activities. So this gives me critical path. 1 to 3 to 4 to 5 is the critical path. So I have identified critical path. Why we are interested in critical path? Because along this path we will be choosing a particular activity to compress, to reduce the duration. But before doing that, we need to compute free floats of the network. So free floats are computed for non-critical activities. So for this 1 to 2 is non-critical. So if you compute the free float here, so this is ESJ minus ESI. So it's a difference between the earliest starting times minus TIJ, the duration written over there. So 15 minus 0 minus 15 makes it 0. So I may recall you here that I told you that for critical activities free floats are 0. But here for non-critical activity also free float can come 0. So there is no problem with that. So there should not be any confusion that the free float should come out to be non-zero always. There is nothing like that. For a non-critical activity also the free float can be 0. And next non-critical activity is 2 to 5. So here free float is 31 minus 15 minus 12. So this is 4. And 3 to 5. This activity is also non-critical. So 31 minus 8 minus 18 makes it 5. So once you have computed all the free floats, we need to compute FF limit, which is the minimum of positive free floats. So there are 3 free floats, 0, 4, 5, but the minimum you have to choose from 4 and 5. So FF limit is 4. So this much is the allowance from the project, from the network, that this much reduction can be done. Now we need to do the other step. We need to figure out one activity on the critical path whose reduction in duration is to be done. And to decide that, we have to compute the slopes of the activities. So computing slopes is our next step. So as you know, this is something I suggested even in the last example, that although at this step I just need to know the slope of 3 activities, critical ones, 1, 3, 3, 4 and 4, 5. But here my suggestion is you compute the slope of all the activities, because later on you will obviously need to even determine the slopes of activities. And slopes are computed just once. They do not change throughout the question. As you can see, the linear relationship is there. So slope is not going to change. So it's better you compute it at one step in the beginning for all the activities. So I have computed the slopes by the formula, the difference in the costs divided by the difference in the durations, taken only magnitudes. And now this is my critical path, 1 to 3 to 4 to 5. So I have 3 critical activities, 1, 3, 3, 4 and 4, 5. So I have highlighted their slopes, because out of these 3 activities I have to select the one with minimum slope. So you can see this 150 is the minimum slope. So I'll be choosing activity 4 to 5 for crashing. And once the decision of activity is decided, once it has been decided that which activity to crash, so I have to compute further its crash limit, that how much that activity is allowing me to reduce. So the crash limit of an activity is computed by the differences in its current duration and the crash duration. So since this is the first step, we have not done any crashing before this step, so the current duration is actually the original duration of this activity 4 to 5. So you can see the difference is 8 minus 5 is 3. And finally I have to compute compression limit. Compression limit is the minimum of FF limit and the crash limit. FF limit we have just computed, it was turning out to be 4, so compression limit is 3. So compression limit is that value which is the actual number of duration to be reduced, actual number of days to be reduced. So I'll be actually crashing the activity 4 to 5 by 3 days. This will overall reduce the project's duration by 3 days. So let's do that. Reduce the activity 4 to 5 by 3 days. So here I have the new project schedule of 28 days. So this was earlier, it was 8. So I have done it 8 minus 3, which is 5. So the activity 4 to 5 has been crashed by 3 days. So, and you will compute the new ES and LC, because when you update the duration on the networks, you have to compute the ES and LCs again. So that will be easy to identify that this time the total project duration is 28. Earlier it was 31, but 3 days reduction is done. So directly from 31 you are coming to 28. So that's the answer to the first part. We have got the schedule of 28 days, and I can compute the cost here. This was the original cost in the previous step, plus 3 is the number of days which you have reduced. It's a compression limit. This should be obviously multiplied by the slope of that particular activity. So the slope of that particular activity which has been reduced means the slope of activity 4 to 5. It is 150, as you can see from the table which I shared before. So this number turns out to be this much. So this is my answer to the first part. I have given the project schedule at a minimum cost which is 4350. And now you look at the second part. The second part of the statement says determine the crash schedule. That means I have to continue this process till I reach a particular point where no further compression is allowed. So let's see how far we can go. So we have to continue now all these steps again and again. So repeat the steps. This is a new schedule. Compute the free floats. So further crashing is required. Yes. Before computing the free floats, I would like to point here one thing. You look at this activity which we have just reduced in the previous step, 4 to 5. Its duration was earlier 8, but when we subtracted 3 days, it becomes 5. And if you look at the question statement, so 8 was the normal duration of this activity and 5 was its crash duration. That means the activity 4 to 5 has actually reached its crash duration. It cannot be compressed further. So this situation will come in the questions when while doing the compression, a particular activity may reach its crash duration. So what we need to remember this, we need to symbolically represent this information in the network. So what we do is draw a star over the duration to make sure that we remember that this particular activity cannot be compressed further. If we have to do further compression, as we are going to do in this question, then I cannot compress activity 4 to 5 because it has already reached its crash duration. The meaning of crash duration is this, that you cannot compress it beyond that duration. So that's why I have highlighted this with a star. Okay. So we need to repeat the process. So first step is you compute the free floats of the non-critical activities. This time it is turning out to be 0, 1 and 2. So FF limit is the minimum of positive FFs, which is 1. So 1 unit I can reduce from the FF limit, the information coming from the FF limit. And now again I have to compute the slopes. Sorry, the slopes I have already computed. I just need to look at which activity to compress. So the same critical path is there, 1 to 3 to 4 to 5, and on this path I have 3 activities, but only 2 are available for crashing because this has already reached its crash duration. So that means this time I have to decide out of these 2, out of 1 to 3 activity and 3 to 4, which one will be chosen. So if you look at the table, we computed the slopes 300, 250, and this is something I've just explained you, that minimum slope activity is 4 to 5, but 4 to 5 has reached its crash duration, so cannot be compressed further. So therefore I have to choose out of these 2. So 300 and 250, the minimum is 250, so I'll be choosing 3 to 4 activity for crashing. And once this is decided, you compute the crash limit of this. So its crash limit is 15 minus 12, which is 3. So if you look at FF limit was 1, just computed FF limit. So crash limit is 3. So compression limit is obviously the minimum of FF limit and crash limit, which is 1. So ultimately from 28 days, I'll be going to a schedule of 27 days. Yeah. So this time you see this change has been made. It was 15, but now this is 14. So with this change, if I'll compute my ES and LCs again, I'll get the final project to be completed in 27 days. And I can compute the cost as well. So this was the original cost 4350 at previous step plus 250 into 1, basically because only 1 day has been reduced. So I have not written that multiplied by 1, but the slope of this activity has been reduced by 1 day. The slope of this is 250. So that's why this is the new cost. So that's the schedule of 27 days. So since you have updated your ES and LC, so there's a point to notice here that this has also become equal. In the previous schedule, if you have noticed, at node 2, ES and LC was not equal. That's why a few activities were non-critical. So this is also going to happen in examples, that as we move towards compression and crashing, new activities may emerge as critical activities. The ones which were originally critical, they will remain critical throughout the network. The critical cannot become the non-critical one, but the activity which was non-critical in the previous step may become critical now. So you need to remember this step. Okay, so here the same thing is happening because of a change in ES and LC. The activities which were earlier non-critical can become critical. So I have seen that this time 1 to 2 and 2 to 5 are also turning out to be critical. And so what is happening? With the emergence of new critical activities, you may get a new critical path. So you have 2 paths now. One path is the same old one, 1 to 3 to 3 to 4 to 4 to 5, and now this is a new path coming, 1 to 2 to 2 to 5. So I have to do the crashing along all the critical paths. Now it will not be sufficient that you do the compression along the one critical path. Howsoever the number of critical paths is, you have to do crashing, you have to repeat the process along every path. That should be clear. And the first step again, so we have to do the further reduction. So I'll be first computing FFs. So there is just one activity which is now non-critical. So its FF is turning out to be 1. So FF limit is 1. So after this, I divide here in 2 paths because I have 2 paths, critical path 1, critical path 2. This is the older one. This is a new one which has just risen, 1 to 2 to 5. So along this path, the minimum slope activity is 3 to 4. You can see here 250. So it's, yeah, so this time I'll be computing its crash limit. So don't look at the table. 15 minus 12 will give you 3. But you know, this is just the original table. This normal duration was the original duration, but with every compression, with every crashing, we are changing the duration of the activities. So you look at the current duration. Current duration means here. So from 15 it has changed to 14. That's why when I gave you the formula to compute crash limit, I told you it is current duration minus crash duration. It is not the normal duration minus crash duration, because normal duration is the original one, but current duration keeps on changing. So when you compute crash limit, so take care of this thing, that the figure here will be the currently available in the network. So crash limit is now 2, and on this path 1 to 2 to 5, slope of 1 to 2 is 200 and slope of 2 to 5 is 125. So 125 is minimum, so 2 to 5 will be chosen for crashing. So to compute the crash limit of 2 to 5, so this is 12 minus 6, which is 6. So now the compression limit has to be the minimum of FF limit and the crash limit, but because now we have two paths, so there are two crash limits. So overall compression limit is going to be minimum of FF limit and the crash limits along the both the paths. So FF limit, which we just saw, was 1. One crash limit is 2, another crash limit is 6, so the minimum is 1. So that means you have to do 1 day reduction, and so you have to crash both the activities 3 to 4 as well as 2 to 5. So crashing each of these activities by 1 day will lead to overall reduction of 1 day. So please listen to this point very carefully. Many of the students are confused. They think that if we are compressing 1 day on one path, 1 day on another path, then overall there might be a reduction of 2 days. That's not true. Overall reduction is going to be also of 1 day. That's why compression along each path is necessary. So you reduce 3 to 4 duration also by 1 day, and you reduced duration of 2 to 5 also by 1 day. So 3 to 4 was this. So from 14 I have changed this to 13, and 2 to 5 was 12. You can check in the previous diagram. I have changed this to 11. So after updating the duration, you compute again ES and LC, new ES and LC. You'll get your new project schedule, and on the similar lines you can compute the cost. That was the original cost in the previous step, 4600 plus 125 is the cost of this activity 3 to 4, and 250 is the slope of this activity 3 to 4, and 125 is the slope of activity 2 to 5. You can verify this data from the table. And 1 day we have reduced, so there is no multiplying factor. So this is new cost. So here we have reached to 26. So let's try whether we can do further. So repeat the process again. Okay, but look carefully here. This time this activity 3 to 5 has also become critical, because 26 minus 8 is exactly turning out to be 18. Up till the previous step, this activity was non-critical, but now this has also become critical. So we have reached a stage, we have a new occurrence of a critical activity here. So this is giving me a new path, a new critical path as well. So I have 3 paths now. 1 to 2 to 5, 1 to 3 to 3 to 4 to 4 to 5, and 1 to 3 to 5. So with the emergence of new activities, you may get a new critical path. So now instead of 2 critical paths, I have 3 critical paths. So the compression needs to be done along the 3 critical paths. So the process remains the same, but I have to compress along the 3 paths. And there is no non-critical activity. All of the activities in the network have become critical. So no need to compute any FF. There will be no free float computed. So actually there is no FF limit. So we just have to decide based on the crash limits. So 3 paths I have. One path is this, 1 to 3 to 4 to 5. One is this, 1 to 3 to 5, and one is this. So whenever this kind of situation arises, you have to make an observation here that how the situation is different at this step from the previous step. In the previous step, our path was 1 to 2 to 5. This was one path, and another path was 1 to 3 to 4 to 5. Means along both the paths there were no activity which was common in them. One path was completely different, another path was completely different. They did not have any common activities. But this time you can see this path 1 to 3 to 4 to 5 and 1 to 3 to 5 have this 1 to 3 activity common in them. So I have to take a wise decision here, because if I choose this activity 1 to 3 for compression, then it will serve the purpose for both the paths. If I choose activity 1 to 3 for crashing, then it will satisfy the requirement of crashing along both the paths, because this is a common activity of two paths. So that's what I'm trying to do. See, for critical path 3, 1 to 2 to 5, because this 1 to 2 to 5 has no intersection with other two paths, so obviously for that the same process has to be followed. You have to find the minimum slope activity, which is 2 to 5, and crash by and find the crash limit of this. But for these two, I cannot simply find their directly individual minimum slope activities. I have to make a decision whether this is beneficial to compress the common activity, or it is beneficial to compress the individual minimum slope activities, because the decision I have to make is should be taking into consideration the cost factor. So I'll be checking this condition, whether the slope of common activity is less than the sum of slopes of minimum slope activities along the paths. Along all paths means obviously these two in which we are making the decision. So I'll be computing the slope of common activity, and I'll be computing individual slopes also, which I have already computed. So I'll just make this comparison. So if this is yes, if it is beneficial to compress the common activity because slope is less. Slope less means the rise in cost will be less in this case. So I'll be definitely going with crashing the common activity. Otherwise, if this condition is not satisfied, then I'll be crashing individual minimum slope activities. So let's check their slopes. So here the common activity which I have identified among two paths is 1 to 3. And individual minimum slope activities, if you identify by looking from the table, so along this path the minimum slope activity is 3 to 4. Along this path it is 3 to 5. You can see the values from the table. So their values are 300, 250 plus 150. So 250 plus 150 is 400, and 300 is definitely less than 400. So that means this condition is true. So therefore it is profitable, it is mandatory to compress the common activity 1 to 3 instead of doing the other way around. So that is how we have to make a wise decision. So this was an exception I was talking about, that see, the first situation arises at the previous step that more than one path is critical. But at that time we did not discuss this thing because there was no intersection among those two paths. But when these kind of paths arises which have the common activities in them, so we have to take decisions like this, that whatever are the common activities, we'll try to compress them, because if this mathematically calculation saves our cost, so we have to take decision according to that. So I'll be crashing this activity, the common activity, and it will serve the purpose for both 1 and 2. Path 3 has its own crashing. It has nothing to do with path 1 and 2. But for 1 and 2, I have chosen 1 to 3. So I'll be now computing the crash limit of 1 to 3, which is turning out to be 3. You can see that from the table. So compression limit is going to be the minimum of 3 and 5. There is no FF limit now. So it is 3. So that means I have to finally reduce this activity 1 to 3 as well as 2 to 5 by 3 days. So 3 days you will reduce 1 to 3 and 2 to 5. So earlier it was 11, now this is 8. Earlier this was 8, now this is 5. You can see the previous schedule. I have done the updation. So and similarly you obviously add the cost. So 300 was the slope of 1 to 3. So plus 300. Okay, wait, I have done a mistake here, so you can correct that. We have reduced by 3 days. Yeah, so this figure should be actually multiplied with 3. I missed that, so you can do the calculations in the cost. So only the cost calculation is wrong, rest all is fine. So here this number 300 plus 125 needs to be multiplied with 3 because the compression is of 3 days. From 26 days we have come to 23 days. So you just check that and update the cost accordingly. So what is important here, after compression of 1 to 3 by 3 days, this has also reached its crash duration. So you can see the data from the original table. Its crash duration was 5, so it cannot be compressed further. So that means if we do want to make further reduction in the duration of the project, then 1 to 3 is out of picture. So I'm at the same situation as I was in the previous step. The only difference is here also I have 3 critical paths, but this time the common activity 1 to 3 is not available for crashing because it has already reached its crash duration. While for this path, obviously still will compute the crash limit of 2 to 5 because it still remains the minimum slope activity. So for path 3 it's still the same, but for path 1 and 2 this time common activity has reached crash duration. So even though the slope was less as we saw in the previous step, even though it was beneficial to compress 1 to 3, but here at this step we cannot do that because it has already reached its crash duration. So here obviously we have to crash the individual minimum slope activities. So 3 to 4 is minimum slope of this path and 3 to 5 is minimum slope of this path. So you find their respective crash limits by looking at their current duration minus crash duration, current duration minus crash duration. So I get 1, 5 and 2. So the minimum is definitely 1. So compression limit is 1. So you crash these 3 activities, 3 to 4, 3 to 5, 2 to 5 each by 1 day. So this will give you a schedule of 22 days. So again I have updated the ES and LC after updating the durations, and cost obviously you need to compute again. Here this number is okay, but this is not right because at the previous step we did a mistake. So you update that and accordingly you can see what is the new cost. So what is important here, I have updated the durations, and now you pay attention to this number, the activity 3 to 4. Its crash duration was 12. So here 3 to 4 activities have also reached its crash duration. That's why I have marked here a star. So you look at the path 1 to 3, 3 to 4 and 4 to 5. This is a critical path and all the 3 activities on this path have reached their respective crash durations. That means along this path no further reduction is possible. We do not know what is happening along other paths, whether it's possible or not, but at least along this path no further compression is allowed. It is not possible. So here we will declare that no further reduction in the project's duration is possible, because if you want a reduction from 22 days onwards, suppose you want 21 days or 20 days, then the mandatory condition is reduction has to be done along every critical path. But at least one critical path has shown up and it is saying okay, you cannot reduce it further, so you will give up there. You have to declare that no further crashing is done. So that's the position which you have to identify mathematically where to stop. Before this point you are not knowing when will this stop. We are just keep going on in the reduction part. So definitely there will come a point where we have to stop, and this is that stopping point. Beyond this you cannot compress further. So this is the crash cost schedule. This is the crash schedule. So I repeat, what is the point which is going to help you in identifying that the project has reached its crash schedule? Along any path, if you are able to identify one critical path such that all the activities along that path have reached their respective crash durations, so there you will declare the crash schedule. So that means we got the answer. This project cannot be compressed further beyond 22 days. And yes, please check the cost value and update it accordingly. So that's all about critical path method. That finishes this topic. Thank you.